Okay, as promised, we're continuing with this example. Okay, so I had f prime of x, and that was negative x squared minus 4 over x squared minus 4 squared. I want to now find f double prime of x. Oh, and let's make a note. This is with the restriction that x is not 0. Okay, so again, I'm just going to use quotient rule. So, low, x squared minus 4 squared. D high, the derivative on top is negative 2x. Minus high, so that's negative x squared minus 4. D low, now I'm going to have to use chain rule for the derivative here. So that's going to be 2 copies of x squared minus 4 times the derivative of x squared minus 4, which is 2x. All over x squared minus 4 squared is to the 4th power. Now before I multiply stuff out on the top, I'm going to factor out what I can. Notice there's an x squared minus 4 here and 2 factors of x squared minus 4 here. So I can factor out an x squared minus 4. Okay. There's a 2x here and a 2x here. I'm going to sort of keep track of what I'm factoring out. Okay. There's a 2x here and a 2x here. I'm going to factor that out as well. If I wanted to, I could factor out a negative as well. I think I'm not going to. I'm just going to factor out this much. Okay. So all of that is multiplied by. Now here, I had 2 factors of x squared minus 4. I only pulled out one of them. So I'm going to have x squared minus 4. I pulled out that 2x, but not that negative. So that's times a negative 1. Okay. And now I've pulled out this and this. So I'm just going to distribute the negative and the 2. So negative 2 times negative x squared is going to be plus 2x squared. Negative 2 times negative 4 is going to be plus 8. All over x squared minus 4 to the 4th. Okay. Would have been pretty tedious to multiply all of this out. So if I can factor some stuff ahead of time, that's really nice. So let's see where this takes us now. So I've got my x squared, oh, you know what? I'm going to cancel an x squared minus 4. So that just leaves me 3 factors on the bottom. So now on top, I've got 2x times, I'm going to distribute that negative. So that's going to become negative x squared plus 4 plus 2x squared plus 8 all over x squared minus 4 cubed. So that is 2x times, this is going to become x squared plus 12 all over x squared minus 4 cubed. That is always defined on the domain. And the only way it could be 0 would be if x is 0, which is not in the domain, okay? Or if x squared plus 12 is 0, which it isn't. So I don't get any new points where this is 0. But just like with the first derivative, it's entirely possible for the concavity to change as we cross to the other side of an asymptote, or as we pass through the location of that hole. So on my number line for f double prime, I'm also marking off negative 2 and 0 and 2. Again, I'm going to make a note that that's a vertical asymptote, that's a hole, and that's a vertical asymptote. So I will not have any points of inflection, because if the concavity changes, it does so at a place that's not in my domain. But let's see. Let's check negative 3. Now if I plug that in, let's see, 2x, that's going to become negative. The x squared plus 12 is always positive. Okay. Negative 3 squared is 9 minus 4 is 5 cubed would be positive. So I had a negative times a positive over a positive. That's going to be negative here. Between negative 2 and 0, I think I'm going to try negative 1. Now that makes that a negative. This is always positive. See, that's going to be 1 minus 4. That's negative 3 cubed is negative. So we have a negative over a negative. So that's going to become positive. Now if I plug in 1, that's positive, but this is still negative. And if I plug in 3, positive, positive, positive. So everything is positive. So we're going to be concave down, up, but just no points of inflection because all of those changes happen with our horizontal asymptotes. So this is very exciting because now we have to play connect the dots. And we don't have any dots. But we do have enough information here because I know that I have to start out close to 0 because I've got a horizontal asymptote here. I know I've got to either go up towards infinity or down towards negative infinity. And if I look at the number line for my first derivative, I can see I've got to be going down. So, I should have even written that in. We're always going down. Okay. So, I've got to start close to the x-axis, but I better start below it because I'm not allowed to cross it, and I'm going to have to come down. Now, between negative 2 and 0, once again, I've got to be decreasing. Oh, and by the way, I was supposed to be concave down. I was forced to be concave down just by the nature of this asymptote. Now, between negative 2 and 0, I also have to be decreasing, but now I have to be concave up. Well, if I'm decreasing and concave up, my graph's going to look something like that. I can start up high. There's no way I can be starting down here by negative infinity. I would have to be coming down like so. Then between 0 and 2, I've still got to be decreasing, but I've got to switch to being concave down as we approach the asymptote here. And then over here to the right of 2, I've got to be decreasing and concave up. If I'm decreasing, I can't start at negative infinity. I got to start up here going off towards infinity. And the asymptotes force me to actually be concave up. And you'll notice I do have this rotational symmetry. If I were to turn this upside down, it would look exactly the same. Now here, I use the behavior of the graph to figure out how to draw it without actually plotting any points. If you aren't comfortable with that, you can always plot points. There's nothing to keep you from saying, you know what, I'd feel better if I knew what the value was at 1. So I'm just going to plug that in. I'm going to get 1. I'm going to get negative 1/3. Oh, I'm negative in this interval. Totally fine to do that. There may be times when you need to do that to get the information, and there may be times when you just feel more comfortable having a couple more points. Totally fine. Okay, back for another example in a minute.